Mineralizing systems. So as Bob said, this idea of a mineral system was first defined in 1994, and that came nearly 20 years after the petroleum industry had already adopted this kind of idea for understanding how petroleum deposits formed. And a guy called Derek Wyborn published the first mineral system paper in 1994, entitled Australian Proterozoic Mineral Systems, Essential Ingredients and Mappable Criteria. And so I'm just trying to minimize something here. Anyway, he defined the mineral system as all geological factors that, that contribute to the generation and preservation of mineral deposits, and stress the processes that are involved in mobilizing ore components from a source, transporting and accumulating them in a more concentrated form, and then preserving them through the subsequent geological history. So basically saying we need to start with metals from somewhere, we need to move them to somewhere else, we need to trap them there, and then we need to keep them there so that we can then find them to then use them for whatever it might be, building electric cars or whatever. Okay. So, in other words, a mineral system describes the full set of geological processes that create and preserve the mineral deposits. And so we need to conclude things like, what are the tectonic events that initiate some kind of ore forming process? We need to think about the source regions. So why are some areas enriched in metals, or the fluids or the magmas that we need to move those metals around? We need a pathway. And so we need faults or fractures or some kind of permeable layer in the case of sedimentary type deposits that allow metal-bearing fluids or magmas to move through the crust. You need to drive that fluid flow. So we need tectonic activity or thermal gradients or something, or chemical gradients, something that's going to drive fluid flow. Then we need to focus those fluids, and we need to focus them into a smaller area to generate a significant ore reserve. And we need to trap those. So we need some kind of mechanism that's going to result in those metals coming out of solution or out of the magma to form a deposit. There can be post-depositional changes. So, for example, migration of metals by exposure to groundwaters make a bigger geochemical halo that we can then use to find that ore deposit. And then we need to bring those mineral deposits closer to the surface, not too close that we shed them away, but close enough that we can find them. And in some cases, as Bob showed earlier, the supergene profile, we can upgrade mineral deposits to make them actually economically viable. And so there's quite a number of proposed mineral systems models. And what we're going to do is we're going to look at a couple of generic ones, and then we're going to look at some examples of deposit type specific mineral systems models. And so this particular one was produced by Dave Houston, and in quite an important paper back in 2016. And so what I like about this one is it's got two axes. It's got time and then scale. And so we go from a large scale, global scale, to cratonic scale, all the way down to the deposit scale. And so at the large scale, we need some kind of way of differentiating the crust. And then we need some process that results in some kind of metal enrichment within the crust or within the mantle. Then we have some kind of tectonic process that then results in fluids that pick up those metals from the source and provides the ligands to move those metals around. And then you can see this arrow is getting narrower and narrower as we concentrate or focus that fluid flow to some kind of trap environment, right? And then you can see a little green thing coming across here. So that's a geochemical dispersion. So that's kind of movement of metals in the secondary environment, might be from groundwater interaction, might be from glaciers moving some formed that deposit, down gradient of down ice flow, some mechanism by which we can use to find the deposit at depth. Okay, so that's a generic mineral systems model. Here's another one that I quite like. This is from the Finnish Geological Survey. I was just in Finland this summer working with some people from the Finnish survey. It's a great agency. So we have at the bottom geodynamic processes. We have a source of metals and a source of transporting agents. We bring those things together. We can transport metals through the crust. And then we need to trap them in a trap environment to make an ore. And then the yellow thing, or the yellow area, represents alteration from those ore-forming fluids, alteration of the surrounding wall rock. And then the green thing again represents secondary dispersion of metals into the secondary environment where we can find them. So that's pretty cool. Actually, I really like that one. So there's 4 major things that we need. So we're going to run through them. So the first thing we need is a fluid source. And the different kinds of fluids we can have, they could be seawater, it could be connate water. So connate water is ancient seawater trapped in sediments when they were deposited. So if we have some Devonian strata over here, might have ancient seawater trapped in their pores. We can have meteoric water, which could be rainfall or groundwater just recharging to the near surface environment. We can have magmatic fluids. So these are fluids that degas as a magma body cools. And then we can have metamorphic fluids. So as we increase metamorphic grade, going from, say, low-grade green schist all the way up to high-grade granulite, so this is basically increasing temperature and pressure. The result of those increasing temperature and pressure is to dewater minerals and force that water out along structures. And that can be another source of fluids. Okay, so we need fluids. Then we need a source of the metals. And that source could be crystalline basement rocks, sedimentary rocks, or magmas, or some combination of all of the above. And so at the figure here is just a basic tectonic diagram showing that we can have fluids coming off the subducting slab, for example, and accumulating metals in the crust, which then get liberated to form archetype deposits or porphyry deposits, and so on and so forth. So, for example, mid-ocean ridges, we can trap mid-ocean ridges with the magmas can be the source of the metals at a mid-ocean ridge and then trap them at surface. Okay, so the metals must be sourced by leaching from rocks or directly from magmas. Then we have to transport those fluids. And there's several ways we can transport those fluids. We can transport them along faults. That's perhaps the easiest way. We can transport them along lithological contacts. So the contact between 2 geological units can be a plane of weakness, which allows fluids to flow along. We can have intrusions which punch their way into the overlying crustal rocks, causing fractures and so forth, or degassing, move fluids. Or in pore spaces, so where we don't have fractures or faults, but we have lots of pore space that are interconnected, we can move fluids that way. Okay. And then finally, we have the trap environment. So there needs to be some mechanism by which the metals are removed from solution or from a magma to form an ore deposit. And these can be changes in pH, changes in the redox state, as we just talked about, sudden changes in temperature, mixing of fluid. And sometimes these are all interconnected. So if we take an ore-bearing fluid and mix it with a meteoric water, the temperature is different, the redox is different, and the pH is different. So mixing of fluids is a good one. We can have fluid unmixing, that is, things become, what's the word I want now? It just escaped me. It'll come to me in a minute. We can have sulfur.
It's called phase separation. So the idea
phase separation. Yeah, thank you.
That you can, if you have a salty water under certain circumstances, it will separate into a saltier brine and a fresher component.
Yeah. And we can have liquid immiscibility. That was the other one I was trying to think of. Yeah. We can have reduction of sulfur. So if we have a brine carrying lots of metals and sulfate, and it reaches a reducing environment, that sulfate can be reduced to sulfide, and the sulfide grabs the metals and precipitates sulfide minerals. Changes in lithology, as I alluded to previously today. So the fluids interacting suddenly with very iron-rich rocks can cause destabilization of the hydrothermal fluid and precipitation of the metals. We can have structural traps and water rock interactions. And all of these things, as I say, are interconnected. And so this leads us to the concept of the concentration factor. So it's not just simply that we move metals by fluids. We have to focus them. We have to concentrate them. And so basically what we do is we take the abundance of the metal in the ore, multiply it by the crustal abundance, and that gives us the concentration factor. So abundance of metal in the ore just means the abundance that makes something economic. All other things being equal, and there's lots of factors that go into whether a deposit is economic or not. So for example, we'll take gold. So the average concentration in the crust is, let's see, that's ppm, about 4 ppb. What do we require in terms of ore grade? We'd like, this is 10 ppm, so we would like quite a few grams per ton, or ppms. And so the concentration factor to go from the crustal concentration to the ore concentration is 2,500 times. For mercury, 10,500 times. For lead, 2.5, and so on. Iron, we don't need much of an upgrade because iron's quite abundant in the crust to start with, and same with aluminum. Nevertheless, we need to concentrate, to upgrade, to make something economic. Okay, so going back to mineral systems models, and so for each deposit style or mineralization style, we can develop a mineralization system model. And so we can break things down into sort of 5 major classes. We have our magmatic deposits. These are deposits that form directly from magmas. We have our so-called magmatic hydrothermal deposits, such as porphyry and epithermal gold. And what these are is represent mixtures of fluids driven off by magmas with some other external fluid to produce magmatic hydrothermal deposits. Orogenic gold sort of sits in the middle. We'll talk more about orogenic gold in a minute. But then we have hydrothermal deposits. And these include volcanogenic massive sulfide deposits, which we're going to talk about in a minute. And these are the ones that form on the seafloor, for example, in the modern system. And so these are generated by relatively high temperature fluids, typically 300 to 350 degrees C. And we have low temperature hydrothermal fluids. So these are our more sediment hosted type deposits rather than volcanic hosted. So these are things called SEDEX, which stands for sedimentary exhalative, and we'll talk about this more in a subsequent lecture. MVT is Mississippi Valley type deposits, and again, we'll talk more about that. But these are zinc and lead rich deposits as opposed to copper rich deposits. And then we have this other class where we have various things like placer gold deposits and so forth, which are formed by erosion or deposition and that sort of thing. Okay, so within this broad context, we can develop a mineral systems model for each type of deposit. So we're going to go through a few of those. So I'm going to go through 4 examples of mineral systems by deposit type, and then just for giggles, here's another generalized ore systems model, which has a little bit more explanation on it for your edification. But again, we have the driving source of ligands, source of metals, we transport to some trap environment. Okay. So magmatic ore deposits, nice big class of ore deposits. So we need to consider the geodynamic and tectonic setting. We need to consider the source and the compositions of the ore forming silicate and sulfide magmas. So silicate magmas and sulfide liquids can become separated, become immiscible. We need to think about the migration pathway of the magmas at a crustal scale, how it's transporting through the crust from melt generation. We need to think of the mechanical and structural mechanisms for focusing magma flow to give us a trap site. And what are the chemical and physical mechanisms for sulfide accumulation and reworking? And then what affects the preservation and the detectability? Because it's an ore deposit is not an ore deposit if we can't find it. And so the figure is a little complicated, but we go from A to B to C to D. So at A, so this is one way that we form magmatic ore deposits. So these are big classes of deposits for, say, chromium, for copper and nickel. Most of our palladium and platinum come from magmatic ore deposits. So we start with a mantle plume, right? And it's beneath the craton. In the context of this paper, it was beneath Archaea and craton, okay? And B, that mantle plume impinges at the base of the crust. In panel C, we then channelize that hot plume material up to the break between two lithospheric blocks, for example, in a suture zone. Okay, so we channel the plume to the thinnest lithosphere at the craton margin. And then finally, in D, so we've got our hot plume, we've got melts that come up along these cratonic boundaries. And so we need the development in favorable and unfavorable environments for mineralization above the melting zone. So as our melts come up, they can form ore bodies if we've got sufficient trap mechanisms. So that's sort of a generalized mineral systems model for magmatic ore deposits. Okay, what about orogenic gold? So gold's, what is it? I didn't look at the price today, but it's around $3,500 an ounce. So gold's an important commodity in economic geology. And many gold deposits, not all, but many gold deposits form in orogenic settings or mountain building settings. And so this is sort of a generalized model of different kinds of ore deposit. And if we take a cross section of plate tectonic regime, so we have an oceanic arc, we get different kinds of ore deposit there. But where we form our orogenic gold deposits is where we have subduction under thick continental crust with lots of plutonic activity. And we have these black lines representing deep lithospheric structures along which gold-bearing fluids can travel and then accumulate gold. And getting into more specifics, so we have our source of metals. We transport those metals through the crust up to the brittle ductile transition. That gives us fractures along which these gold-bearing fluids can flow. And then when we hit different rock types, different redox boundaries, we can then precipitate that gold out of solution. Okay. What about porphyry and related? So this is a really complicated diagram, but because there's a lot of different kinds of ore deposits that form in subduction zone settings. But the biggest class is our porphyry deposits. And so here we have a model for the formation of porphyry copper deposits. We have a magma intrusion, we have degassing of fluids, mixing with meteoric fluids coming down and forming our ore deposit. So just the other kinds of deposit here, we have things that are more high level, but all of them are fundamentally rooted in the degassing of magmas, mixing with meteoric waters, and forming our ore deposits. Now this table, there's two panels here. So it goes from bottom to top. And the details aren't really important, but this was put together by a guy called Jeremy Richards, who died pretty much when this paper came out. And what he tried to do was he tried to formulate, using a systems model, how hard it is to form an economic deposit. So for porphyry copper, in this case, for porphyry copper deposits. So what do we need? We need subduction of oxidized hydratic oceanic lithosphere. That's great. So in some cases, we will produce an infertile arc because it's too reducing. So we come up. So we get 90% preserved. We need a long-lived, moderately steep subduction system leading to focused magmatic arcs. Great. We get 20%, satisfy that. And then we go up and there's 10%. And then we need transpressional strain and so on and so forth up till we get to a 0.0001% chance of forming a very large economic porphyry deposit. So again, the details aren't important. The point is that the systems model that Jeremy put together basically led him to the conclusion that the formation of a large economic deposit is extremely rare. And that's why they're worth so much money. Okay, what about VMS systems, just to close off? So volcanogenic massive sulfide deposits form on the seafloor, and they can form in a failed rift where we have seawater. They can form in a mid-ocean ridge here. They can form in an island arc, in a rifted forearc, in a rifted arc, or in the back arc. Okay, so a lot of the VMS deposits form above or behind subduction zones. And they can form in mature arcs, either in the back arc or the extreme back arc. And so what we need there is we need seawater. That's fundamental. So this is sort of zooming in a little bit. And this is showing that we need a magma chamber at depth to drive the heat, and possibly magmatic volatiles coming off the magma chamber may be involved, although people argue about that. We need seawater to come down along structures, get heated up by that magma source, and in doing so, leach metals from the rocks to make a hydrothermal fluid. So at this point down here, the temperatures are probably around 400, 450 degrees C. Modified seawater reaches its maximum buoyancy, and it wants to rise up. And as it does, it interacts with the surrounding rocks to form sulfide minerals in the subsurface, or those fluids mix with seawater to form sulfide deposits right at the seafloor. And this diagram just shows several different environments where these kinds of deposits can form. This is sort of a regular type, sort of a generic model. They might be a chemocline. In other words, there might be oxic and anoxic ocean waters, which can help form sulfide deposits. There might be subsea floor replacement deposits. Okay. And so zooming in, just to sort of focus that in, we have a crystallizing subvolcanic intrusion. That's our source of magma. You can see the temperature gradients here, sort of greater than 400, right around the magma supply. The temperatures decrease as we come up. Fluids come up along these structures and form hydrothermal systems at the seafloor. And then just to zoom in right to the deposits themselves, what we typically have is this stockwork or feeder zone, which is lots of veins of high temperature sulfides. And then we form a mound, which is basically the coalesced fragments of chimneys that when they die, they collapse, and we form a mound, which is composed of fallen sulfide chimneys composed of zinc sulfides, lead sulfides, and copper sulfides.